Hello everyone. This presentation discusses the design and analysis of a ballistocardiographic cardiospectral fingerprint using MATLAB and Power BI. This work was conducted as part of the course and focuses on applying signal processing concepts to biomedical data analysis. Ballistocardiography is a non-invasive technique that captures the mechanical response of the cardiovascular system. Unlike electrocardiography, which measures electrical activity, BCG reflects body motion caused by blood ejection during the cardiac cycle. This makes BCG suitable for unobtrusive and long-term cardiac monitoring. This project uses a publicly available BCG dataset recorded from 32 participants using piezoelectric sensors. Reference heart rate and respiratory signals were provided for validation. Hospital visit in Jordan showed that ECG is widely used, while BCG technology isn't yet commonly adopted in clinical practice. Despite its advantages, BCG signals are difficult to analyze. They are low in amplitude and highly sensitive to noise, respiration, and motion artifacts. Therefore, advanced signal processing is required to extract meaningful physiological information from the signal. To enable structured analysis, the BCG signals were segmented into non-overlapping 10-second windows. Each segment is assumed to be quasi-stationary, which allows meaningful frequency domain analysis. Segmentation also supports comparison across different time intervals. From a signals and systems perspective, the BCG acquisition process can be modeled as a linear time invariant system. Cardiac mechanical activity represents the system input, while the measured BCG waveform represents the output. Noise sources act as additive disturbance.
Hello, my name is Tariq Ashman, and I'll be continuing this presentation from this point onward. In this stage of analysis, digital filtering was applied to improve the quality of the BCG signal. A high-pass filter was used to remove the baseline drift caused by slow body movements and respiration. At the same time, a low-pass filter was applied to suppress high-frequency noise and sensor-related artifacts. After filtering, the cardiac-related components of the PCG signal became significantly clear, which is essential for accurate frequency domain analysis. Once the signal was filtered in the right way, analysis was performed in the frequency domain. Each 10-second segment was transformed using the fast Fourier transform. The resulting magnitude spectrum and power spectral density allowed us to observe how signal energy is distributed across different frequencies. The analysis revealed dominant low-frequency components that are associated with mechanical cardiac activity rather than noise. To extract meaningful and compact features from the frequency domain representation, spectral magnitudes were averaged within predefined frequency bands. The analysis focused on the 0 to 0.45 Hz frequency range, which captures the most relevant mechanical cardiac information. This range was divided into 10 uniform bands, each representing a specific portion of the spectrum. These bin averaged values form a numerical summary of each PCG segment. The extracted spectral features were then organized into what we call cardiospectral fingerprint. This fingerprint is represented as a matrix, where each row corresponds to a time segment, and each column corresponds to a frequency bin. The value within the matrix represents the average spectral magnitude. This structure allows us to visualize how the spectral characteristics of the BCG signal evolve over time in a compact and interpretable way. To enhance the comprehensibility and explicitity, the extracted features were exported from MATLAB and integrated into a Power BI dashboard. The dashboard includes multiple visual components, such as time domain plots, filtered signal comparisons, frequency spectra, and a heat map of the cardiospectral fingerprint. Interactive slicers allow the user to explore individual signal segments, making the analysis accessible to both technical and non-technical audiences. Results demonstrates stable low-frequency spectral patterns across most signal segments. Digital filtering significantly improved signal clarity, which was reflected in both time domain and frequency domain representations. Minor variations between segments were observed and are attributed to physiological variability and residual noise. Our future aim may include real-time PCG acquisition and integration with wearable systems. In addition, machine learning techniques could be applied to the extracted features for classification and anomaly detection. Further clinical validation and comparison with ECG-derived features are also recommended. This project was completed by Tara Khashman and Christina Bairuti as part of the BME 362 course. Thank you for your attention.